presentation. So far you heard the scientific part of the presentation, and now comes a much simpler and direct presentation. We are also involved in coatings and linings. We are involved in thermal insulation. We are involved in refractory linings and also fireproofing. This is a picture of a refinery, and you see that insulation is almost everywhere. So I give you a little sense of the value. I talked to our estimating people, and they told me that the value of these items are, for a $100 million investment, you pay about $2 to $3 million for the painting. You pay $5 to $6 million for the thermal insulation. The refractory lining is dependent on the unit. Some use almost nothing, and some have it only in heaters. But then there are other units, like our Klaus units, which have expensive and lots of refractory installed. Fireproofing also depends on the amount of hydrocarbons being present in the unit and can get involved in the fire. Having said this, so the total investment cost for this for these items can be easily up to 20% of the total investment cost if you add galvanizing, special coatings, and these kind of things. Having said this, this is a plant currently under construction in Canada. It's a gas plant, and the client elected not to paint at all, or very limited painting. He only paints, here's the red point, he only paints hand railing, ladder, cages and ladders. He paints some other safety items, but the majority of the plant will not be painted. Like all the structural steel and the piping, which is not insulated, and equipment and vessels will have no insulation and no painting at all. So it will have the nice rust look after a while. But this is located in Alberta, Canada, in a remote location, which might be okay because rainfall there is only less than 10% per year, and external corrosion is really no big issue and will not reduce the service life of the plant by a big amount.
What about like where these refineries are close to the ocean? Is there additional corrosion allowance added?
No, we always paint. I mean, this is really the exception. Most clients paint their plants, especially if they're close to water and especially close to the ocean.
Even the structural steel?
The structural steel is always painted, yes. By the way, this plant has also no fireproofing whatsoever.
Is galvanizing considered painting?
Galvanizing is one of the corrosion protection systems, and we're going to touch on it briefly. This is a picture of a local refinery, and I want to show you where you find these items we are going to talk about. This is a fired heater, flue gas ducting, and a stack. You find refractory lining in these items. Then you see insulation on the columns, on the vessels, on heat exchangers, like here. And you see also insulation on piping. Almost everywhere. There's fireproofing on the structural steel and on vessel skirts. There might be some linings inside the vessel. So you find these items throughout the entire refinery.
Actually, that first level is actually it's a concrete.
This here is most likely solid concrete, but you can see that from this point up they used a different fireproofing material. For cost reasons, most likely, and there's less likely damage to these areas here. Let's first talk about coatings. There's a reason for coating. We're going to talk about types of coatings and how they are arranged into systems, how we select the coating systems, and the application, and some issues with specification and some general points. The majority of items in refineries is made from carbon steel, as Ardo mentioned. It's a prominent construction material. material, but it has the disadvantage that it tends to rust and look pretty ugly. So we are putting a coating on this carbon steel to prevent this rusting. It's really a barrier between the steel and the environment that prevents the chemical reaction that will take place normally between iron, water, and ions, as Adel explained earlier. So this is really a passivating layer that prevents or reduces atmospheric corrosion. Coatings can be applied to the inside or outside. Inside, we call them normally linings, and they're normally more sophisticated. Then, of course, we paint for the looks. It is, I think, nicer to work in a well-maintained and painted place than in a shabby old run-down place. But it doesn't work out always. Could you show me the picture? This is, of course, a sulfur recovery unit, old, a very severe environment, and it's very difficult to maintain this nicely. The steel might have been painted at one time, but it's hard to tell by now. But I think this is daily life in refineries. On the other hand, this is a new plant, nicely painted, everything nice color scheme. They used black for the hand railings, they used blue hand wheels, so kind of impressive and nice to look at. And the third reason we are going to paint is for safety reasons or for identification. There are standard safety colors, which are almost national standards, and the client decides how to apply them to his unit. And the local refineries, in this case, again, Chevron Richmond, they go in more detail and explain how they're going to label the entire piping system by colored band in this case. In some cases, they paint the entire line with a certain color. And here again, this is the way it looks in real life. Again, this old Klaus unit, but you see that this yellow line is a hazardous line. It's most likely a hazardous gas. And next to it here is an insulated line where they painted the insulation jacket and showed the fluid, which is, I think, H2S. Here's a blue line, or some blue lines, which are most likely nitrogen lines. So even in an old plant, it gives you distinct, points in regard to safety. Now the painting types. Paint typically consists of a solvent, also called a volatile organic compound, a resin, and a pigment. The solvent keeps the paint liquid in the can, and during application, once it's on the surface, the solvent evaporates and the resin is left behind, and the pigment is embedded. The pigment is in many cases a metallic pigment that acts like the anode for cathodic protection. And most paints industrial paints are two-component paints. You need a hardener or an accelerator in addition to the solvent. The solvents or the VOCs are controlled by the air quality management people, and they just recently reduced the permissible amount of solvent in the paint to 10% per 10 grams per liter. Sorry, 100 grams per liter, and this gives a hard time to the paint manufacturers. Quite a few paints cannot be used any longer, and we have to find different paints. So the industry is inventive. There are now many paints which are water-based paints, or they have no solvent at all, and can be then applied under strictest rules. Can you click on coating chart? Here's a listing from one of our clients, Chevron, I think, that lists how paints are performing. They're giving on the left column the generic type of the paint, and then the type of cure, how it performs under sunlight, and some other performance criteria, a guide for us to select the right paints. Recently we got involved in powder painting, powder coatings, which are typically used only in factories normally, but our client is in North Slope. He wants us now to paint, to use powder coatings under insulation, under in the piping, which is a fusion bonded epoxy in this case, but there are many other chemicals that can be used as powder coatings. There are laminates, which is a combination of a normal paint or a regular paint reinforced with fiberglass, either shop fiber or a fiber mat. These coatings are pretty thick, durable, and abrasion resistant. A completely different type of coating is hot dip galvanizing. Please click on the. This is a 4-step operation. There's a caustic bath where you put the part in to get all the grease and grime and dirt off. You rinse it. The next step is pickling. It's normally hydrochloric acid, and this takes all foreign layers off the surface down to bare metal. After this step, it's again rinsed. Then flux solution is applied, and finally it's put into the molten zinc bath, where the molten zinc is deposited on the piece. The zinc bath is about 730 degrees F, so you have to design your piece to be able to take this kind of temperature, and distortion is quite an issue there. So you have to design for hot dip galvanizing. Here is a bigger structure, completely hot dip galvanized. I think this is a air cooler enclosure we used at the North Slope. Then another method to apply metal to carbon steel surfaces is metal spraying. In the past we used aluminum and zinc, and this process is very simple. Wire rod is melted in a gun, and then the molten metal is propelled with air onto the surface, which was prepared before to accept this metallic coating. Okay, the paints we arranged into coating systems, which is a multi-layer application of paint. Typically there's at least a primer and a top coat, but the preferred method is a primer, an intermediate coat, and a top coat. The top coat is mainly there to preserve the appearance of the coat, to keep it glossy. In this case, we use quite often urethanes, which have excellent resistance to UV, but also epoxies are used. Here is all these systems, of course, the temperature dependent, so we have to make system for each temperature range, and also quite often for location. Here is a typical client coating system chart. In this case, he allows 3 different paint manufacturers, Carboline, Devaux, and International Paints. And then on the left-hand side, you see the operating temperature ranges, and then he tells you how to prepare the surface and how to coat it. As you can see in the Carboline column, there's Carbozinc, Carbozinc, Carbozinc. So the primer is uniform, which makes life easier. You can paint everything with the same primer, and then can decide later how to top coat it. You also have to consider the coating compatibility between the different paint layers. Not all are compatible. This is given by the coating manufacturer quite often. linings are applied internally, and they are more sophisticated. They are exposed to higher temperatures typically. They are in the merchant service, and it's more important to keep them in excellent condition. And here is, again, our client's view on what to use. In the left-hand column, he gives us the trade names and the generic names of the coating of the lining system, the anchor profile, the dry film thickness, and the total film thickness. Click again, please. And also, in this case, how to apply it by temperature, pressure limitations, and then partial pressure of CO2 and partial pressure of H2S limitation. Here gives another guide for which surfaces these linings are applicable. It's my turn. So when we select coating, we have to think about chemical resistance, compatibility, temperature limit, damage resistance. Quite often we paint very early in the shop, so we have to transport these things, and they might get damaged during transit. And some paints are better than others for this purpose. The performance under atmospheric conditions, the regulations. Just recently, most of the paints Chevron has in the catalog cannot be used because they have too much solvent in the paints. Once in a while we think about economics, and then the application methods, and of course client preferences, what the client wants he gets, as long as it's reasonable and technical okay. Here's the economic part of it. Occasionally we have to do a life cycle cost analysis where we balance the installation cost plus the maintenance cost versus benefits over the lifetime. And it is quite often the case that if you spend more money up front, overall you gain money by not having to paint so early again. The client specifications we use frequently are really also a copy of the manufacturer's data requirements, and they tend to be a little more conservative than the manufacturer's specification. Coating application is really a two-step process. We have to prepare the surface, make it clean for the paint, and then apply the paint. Here is cleanliness specified, is given by NACE standard and also by SSPC, which stands for Steel Structure Painting Council. And if you see here that abrasive cleaning methods are 7, 6, 10, and 5 by degree of cleanliness. It goes from just a brush-off blast cleaning to a white metal blast finish. And the tool cleanings go from SP2, which is just a hand tool cleaning, wire brush, chipping tools, over power tool cleaning. And there's a method now, SP11, which cleans to bare metal. All cleaning operations are normally preceded by this SP1 to remove all oil and grease and these kind of things. The cleaning results in an anchor profile, which is typically 1 to 4 mil thick, which is the distance from the top to the average distance from the top to the bottom of the valleys here. And it's important for the paint's performance. Too low might be poor adhesion. Too high, the peaks might stick through the paint and you get rust bloom again. And this is measured during inspection with a special tape which is impressed over the surface and then measured with a caliper to get the right thickness or the right range of profile. Can you click on abrasive? Here's a list of abrasive that can be used for abrasive blast cleaning. It's not complete, but it's a good portion of it. I remember a job where we used crushed walnut shells to clean because it was the only abrasive we could use to clean the surface gently. The paint is applied typically by airless spray, by brush or roller. Airless spray what we prefer because it's the fastest method. But in the field, quite often we cannot do this because of concerns overspraying other items. So quite often we have to brush paint entire plants with a much slower method. We try to apply our paints in the shop as much as possible because it's less expensive overall, even though you have to allow for additional expenses for touching up the shop coatings in the field. But there, of course, there are some coatings which only can be applied in the shop. Here are the testing requirements. There are many more than this, but here are some typicals. Typical is holiday testing, where we test the surface for any pinholes and imperfections. It's electrical resistance test. We test for the dry film thickness, which is the thickness of the film after it has dried, of course. And then the other tests like air temperature, dew point of air, surface temperature, ambient temperature. We test for make sure that the air used for blasting is oil-free. We also test adhesion once in a while or other items. Could you please click on the test equipment? Here are some typical tools the inspector uses. There's a wet tip. There's a wet thickness gauge. This is a set of plates that show how a surface should look once it's prepared to a certain anchor profile. Here is high voltage Holiday inspection tools. Here's a brush attachment, or you can have a ring attachment for pipes, or this kind of brush for inside pipes, or a different kind of brush again. This is done up to a voltage of maybe 7,000–8,000 volts to test for imperfections according. Here's a thickness gauge that measures the dry film thickness, and here's a device that determines the dew point of ambient air. It just measures the dry and wet bulb temperature and determines the dew point. Again, we are using our client specification most of the time, but occasionally we have to write our own. So in general, carbon steel is the most used material in refineries. Exposed steel is typically coated. We paint under insulation only if the temperature is low. At high temperature, we don't paint because there shouldn't be any water. Stainless steel is not painted. However, it's painted under insulation to prevent chloride stress corrosion cracking. I think that was a part of coatings. Now we go over to insulation. And this here is a design used in eastern Siberia to keep a oil line warm. And I can see the inspector likes the performance of the insulation. Can you go back to slide 2? However, our insulation looks like this. Which is, of course, an insulation material and a weather jacket on top. This is typical application method used in the United States and Canada. This one here, I can tell from looking at it, it's overseas, most likely Australia or New Zealand. They're using a slightly different method of doing the sheet metal work. Can you go? Yes, next one. Okay. Okay. The reasons for insulation, there are some benefits. It can reduce the heat gained or lost to the environment. In reality, any of our refinery processes will work without insulation because the heat transfer inside the unit is so big compared to the losses you can have over the uninsulated surfaces to the outside. However, if you look only at the heat loss from the surface to the ambient, you save about 95% of the heat. So the insulation is quite effective there. It helps with the process stability. I remember a case where we couldn't finish the insulation. It was a hot process, and the unit got into a heavy rainstorm, and they couldn't control it because the temperature changed too fast and too drastically. And of course, insulation protects people from hot surfaces. When we select insulation, we consider the weight because it's a factor in the stress analysis of piping. Damage resistance, there are many cases that the insulation was damaged before the construction was complete. We make sure materials are compatible amongst themselves, but also compatible with the surface to be insulated. Very important, the K factor or thermal conductivity, which determines the insulation value of a material. And again, client preferences. Client have their own opinions about what to use and not to use. I think here we have categorized the insulation by types, by insulation type codes. We have hot insulation typically used for heat conservation. Then there's a special kind of hot insulation where we have electric tracing or steam tracing involved, which is a heater on the pipe or on the equipment under the insulation. We have cold insulation, which reduces the heat transfer from the ambient to the system. This includes a vapor barrier to make sure that we don't get water into the insulation and we don't form condensation on the insulation. We have personal protection insulation, that's the safety issue. We use acoustical insulation, which reduces the noise from the surface and is quite often combined with heat conservation or cold insulation. We have to optimize insulation thickness. There are the economic insulation thickness. Can you show the graph, please? Here's how we determine the insulation thickness. There are two basic functions. One is the annual heat loss cost, which is this function here. So if you insulate thicker, you spend less money for the heat lost. On the other hand, if you insulate thicker, you spend more money for the insulation. You determine the sum function, and where the minimum of the sum function is, this is your economic thickness. Can you go back? This sounds pretty simple. However, on the heat loss side, we need to know the fuel costs, and they change all the time. We have to know the investment, cost of money, interest, depreciation, maintenance, number of operation hours. All these things are kind of iffy quite often, so the entire thing becomes more or less a good guess. On the insulation side, it's the investment cost, and again, when we do this analysis, it's very early in the project and the prices are not firm. So the entire thing is a tool to find something which is reasonable, but it's not really a scientific approach. Let's go back in. Okay. Quite often we have to limit the heat loss to a certain value from the insulation surface. Another optimization is to extend the cool down time of the fluid that is being insulated in a pipe or a vessel, and we have to limit condensation in steam systems. On heat rate systems, it's the same type of thing. In addition, we can optimize the number of tracers versus a thicker insulation. So in some cases, you might want to insulate thicker and save a tracer and be overall ahead. And on this heat rate system, we have to balance the heat input from